right, so now we're going to look at the effect that having a solenoid, basically, that undergoes changes in magnetic flux with current and is going to have an effect on circuits. So to start this topic off, we're going to talk about the idea of mutual inductance. So let's say we have two solenoids. We have solenoid number 1 over here, which has a current that is running through it. Okay, so current is running in through number 1 right here. Okay, so we have current coming through. So if we were to follow that current around, it's coming up through the back and up over the top. So if we curl our fingers around that, our fingers come up over the back and over the top. Our thumb points to the right. So this one right here is creating a magnetic field to the right. Well, now this second solenoid is not connected to a voltage source. So it doesn't have its own current. However, if I change the current that is flowing through this first inductor, what ends up happening is that is going to change the magnetic field. And if the magnetic field strength changes, we have an area here for our loop. So there is going to be a flux change through wire 2. So is I change that current, I'm going to have a change in flux. If my magnetic flux changes, then we know that what's going to end up happening is we are going to induce a current in the second wire. So we're going to get some sort of I induced here, depending on what is happening to that flux, whether it's going up or down. So what ends up happening then is that this coil will then have a current. Well, let's say that our magnetic flux increased. Okay, so we increased the strength of B1, so our flux increased there. Well, what happens is I'm going to need a flux that opposes the change. So my B induced must be in the opposite direction of B0, in this case B1. So I'm going to get a induced magnetic field, for example, in this wire that is in the opposite direction. That's then going to create a current in this wire that is in the opposite direction, or the other way. Well, that's how you find it. But that induced current is going to create that opposing magnetic field. That now then create that magnetic field then passes back through this original coil. So that is going to cause a decrease in flux for this one because it's creating a magnetic field in the opposite direction. And so its field was going the opposite way. And then that's going to change what's going on in this one. So these two coils are going to be constantly affecting each other. This is called mutual inductance. Well, it's all going to be based on flux. But what's kind of crazy is we don't even need the second solenoid. A solenoid on its own can have its own induction effect, and that's called self-inductance. A changing current in a coil can induce an EMF in itself. Okay. So how does this work if there is not a second coil? Well, if there's no changing current, then there's no changing flux. And then this solenoid just acts like a solenoid normally would. But what happens if you actually change the current? So if we change the current, then this thing on its own has its own area A. And so the magnetic field that it itself is producing is then changing. So let's say I'm actually increasing I, then our B's increasing, so the flux through itself is increasing. So that is then going to induce a current and an EMF that has to oppose that change. And so what we end up getting is we get what we call a back EMF, because in order to oppose the change, we have to have an induced magnetic field in the opposite direction as the original field. That's going to create an induced current that is in the opposite direction of our original field. So we are going to get this back EMF. So this solenoid is essentially going to fight itself. So this self-inductance, which we're just going to call inductance from now on, is going to be represented with a capital L. The unit is the Henry, which is a capital H, named after the guy who figured all this out. And it is based on flux. So the magnetic flux through that solenoid is going to be the product of L and I. So L is going to be based on the physical construction of the solenoid. Kind of like our resistance, if you think about that, resistance is rho L over A, so it's based on the physical construction of the resistor itself. When you put a resistor into a circuit, its resistance stays the same. That's going to be the same as the inductance. The inductance is kind of like resistance, but for an inductor. And it's also based on current. So our flux is based on L and I. So if I have some sort of solenoid here that has an L, and I have a current that is running through it, my magnetic flux is bigger the larger L is, okay? Or if I take an L and I increase the current, I'm going to get a larger flux. So this tells us that our induced EMF is equal to negative L, which is our inductance, delta I over delta T. Now the negative, remember, just tells us oppose. It means the opposite direction. Where does this actually come from? How do we get here? So Faraday's law says that E is negative N change in magnetic flux over the change in time. Now, there's no N in this particular equation, and the reason is that when we look at the formula for L for a solenoid, L actually includes the number of loops. So we can ignore it here because it's going to be taken into account in our flux calculation. So we just get negative change in flux over change in time. So if we sub in L times I over a change in time, if we're assuming that our inductance, L, is due only to the physical construction, then once I put that into the circuit, like, it can't change. So I can pull that L out in front. So I get E is equal to negative L change in I over change in time. And really, all I'm going to do is in my circuit is change currents. So the currents are the only thing that's going to change over time. So this tells me that my induced EMF must oppose any change in current. So looking at that negative tells us the EMF that is created opposes the change in current. So that's usually called the back EMF. The back EMF is what creates the induced current. Okay, so it's back EMF. It's like the EMF that is in opposition to the change. So whenever I say inductance, I'm actually talking about self-inductance because we're going to be talking about one solenoid. Now, what is the inductance of a solenoid? So I said it was based on the geometry, the physical construction only. So if I have a solenoid which has a cross-sectional area A, okay, that would be the circular area of a cross-sectional loop, a length D, okay, so we're using a D here instead of L because L for inductance gets confused with L for length. So that's the length of the loops. And we're going to have a turn density, N turns per unit length. So that is going to be N over D, actually, is going to be little n. So that's the number of turns. So N is the number of turns over D. That turn density is often how like solenoids are produced. You could actually change this up a little bit if you plugged in, but this is the way that is generally written. So L is our inductance, is based on mu naught. Mu naught is that magnetic permeability of free space, 4 pi times 10 to the negative 7th. N is our turn density, so the number of loops per length. A is the cross-sectional area, and D. So we can see that if we were to actually sub this in over here, we can change this up a little bit. We get L is equal to mu naught N over D squared A times D. What we would see is the D on the bottom, actually it doesn't quite cancel there. Let's distribute that. Mu naught N squared over D squared A times D. What actually ends up happening is when the D's cancels and we get mu naught N squared A over D. So the number of loops is a huge factor here with solenoids. So when they make the inductors, they make the wires to get really large inductances. They use the thinnest wires that they can. They have to be insulated so that they're not actually touching. So they just do a very, very fine coating so that you can get as many wraps as you can in a very, very short distance. A is our cross-sectional area, so the bigger it is, the bigger the inductance. But big is a problem for circuits. If I'm trying to make a circuit board inside of a computer or something, I need that to be a small component. So getting the number of loops up is a really effective way to increase the inductance. I can also see that if I have a really large loop, if it's really, really long, that actually causes a smaller inductance. But it's kind of that balance, the idea of this N over D, because I do want to make them more compact so I can get more N in, but there's kind of this competing factor here. So basically more turns per unit length is going to have a big impact. That's going to be the biggest thing. Now, this depends only on the physical construction, not on the current passing through. So inductance is a constant for a device. So you can go out and buy an inductor and printed on it will be the inductance L. So that is going to be how we find the inductance. And then this guy is now called an inductor. Kind of like a resistor is something that has resistance. An inductor is something that has inductance. So this is a device that you will put into a circuit. So now we're going to see what happens when we put an inductor into a circuit. Now, just so you know, like this circuit doesn't really show it right, but the symbol for an inductor is usually something that looks like this. Usually has 3 loops. That would be the symbol for an inductor. We're not going to do tons of calculations and things with inductors. We've already got a lot going on. I really want to focus on the electromagnetic induction concepts, and we're going to do much more conceptual on average for our inductors and circuits than we did in our circuits unit. But that's what you would expect to see if you get a circuit question with an inductor. It's not going to look like that. It's going to look like this. Okay, so that really should be there for that. So what we have here is a circuit. So we've got basically our voltage source. Okay, so we do have like a battery or something that we are connected to. We have a switch that initially starts open. We have an inductor and we have our resistor. Of course, if the switch is open, then no current is going to be able to flow at all through this. So what we're going to do is kind of like what we did with capacitors. We're going to figure out what happens to our current when we add this inductor into the circuit. I know that if there was no inductor, that what would happen is my current would automatically come on. So if I start a timer, and this is the current through my resistor, and this is time, that if I just left the switch open and I started a timer, I'd have no current, I'd have no current, I'd have no current. And then the instant I close the switch, my current would just jump up and it would just be on. Okay, if I just had the resistor, that's what it would look like. Well, what happens though is when I close that switch, you are going to be running a current through that inductor. That inductor has a cross-sectional area, so that current is then going to create a magnetic field. And so that magnetic field is going to oppose the change, and it creates a back EMF. So back in opposite. So if my current is running to the right, I actually get an induced current that is in the opposite direction. So EL is basically that back EMF. So it's in the opposite direction. So because it's opposing my current, what happens is instead of having this big jump, so my little diagram disappeared. So there's my I and there's my time. So instead of having just this jump when you close the switch, we get this back EMF. Now that jump is a huge rate of change of current. So that means I'm going to get a very large back EMF. And actually, if you were to look at the slope, a rate of change is a slope. The slope of this jump is essentially infinity. So you get kind of this back EMF that completely blocks the current at the time that the switch is closed. So at the time the switch is closed, instead of jumping up, my current stays 0. But over time, the change in current kind of flattens out. So we kind of get it to flatten out here instead of getting a jump. So the slope of this graph gets closer and closer to 0 over time. So my induced EMF is going to get smaller and smaller and smaller until my current is approximately steady. And then we call that a steady state because our current is effectively constant. And if my current's constant, then my rate of change is 0, my back EMF is 0, and this guy basically behaves like a wire. Over time. So over time, my inductors behave like a wire. But at the first instant, we get basically this complete backflow. So after a long time, we reach that steady state current. So at the instant the switch is closed, my inductor completely blocks the current. So our I is 0 at this instant. And basically the voltage of my inductor is equal to the voltage of my source. There's no current flowing through. However, over time, the rate of change of the current over time is going to flatten out and it's going to steady out. And my induced EMF, my back EMF becomes 0 and my induced current becomes 0 and my current reaches steady state. So as t approaches infinity, my inductor just acts like a wire. With 0 resistance. So an ideal wire. This is the opposite of what capacitors did. Capacitors, when they were uncharged, behaved like a wire. So if I had this uncharged capacitor here and I was to close that circuit, then I would get a full current at the start, and then as the capacitor charged, my current would decrease until a capacitor blocks current when it's fully charged. My inductor does the opposite. At t equals 0, when that switch is closed, it completely blocks the current, and then it slowly allows current to flow until it reaches a steady state. So what ends up happening is when you first close that circuit, you are going to get this smoother curve. This curve has another time constant with it, tau. Tau is going to be L over R. So remember, for a capacitor, tau for a capacitor was equal to R times C. They were products. In this case, my resistance is in the denominator. So what this tells me is the bigger my inductance, the longer it's going to take until I reach steady state. The more resistance I have, the smaller the time constant is going to get. And that's going to be easier for it to reach because my currents are going to be smaller with a larger resistance, so there's not going to be as much opposition. So why would I do this? Why would I put a device that blocks current? Well, if you think about it, your electronics are very, very delicate. They have the capacity, the little tiny, very thin components are really easy to burn out. So inductors are used in circuits to help prevent power spikes. They're useful in like in surge protectors because I don't want my current to jump up. If I don't have a current and then my current jumps up and turns on right away, then that could damage the components that I have. So instead, it creates just this small increase. It doesn't have to be a long time for it to charge up, but it just creates this more gradual increase in current, so it's less of a shock to the components. Now, if this just keeps like that forever, then basically my current will stay at steady state. But just to kind of see what happens in the opposite, if I was just open the switch, well then no current would flow because there's no there's not a closed circuit. So let's imagine that we kind of mix this up and I open the switch but then connect this extra wire here so I still have a loop. Well, what ends up happening is I had a current that was flowing through and it was at a steady state. When I connect this wire, I'm removing the voltage source. So if this was my current over time, if I don't have the inductor in there, I would have had this current. And when I open that switch and connect the wire, I would just jump back down to zero. But once again, the opposite is going to happen because by having that inductor here, what ends up happening is that when that current drops, the inductor resists that change. And so there isn't a power supply in here at all. So how could current flow? Well, basically this inductor has been storing energy in the magnetic field. Magnetic fields store energy. And what happens is our inductor actually becomes the voltage source. And that back EMF actually changes directions because now I want the flux passing through that loop is going to decrease if I drop the current. So my inductor is going to oppose the decrease. So I need a current that is in the same direction as the original current. So what happens is this inductor becomes the voltage source. But it's going to lose energy over time because all that energy that's stored in that inductor is going to pass through that resistor and it's going to be converted into heat. So what happens is instead of getting this sharp decrease, this thing is slowly going to decrease over time. And you're going to keep the same current at the instant our little circuit is completed without the voltage source, but it will slowly decrease to zero. So once again, we're avoiding that really sharp decrease that could cause damages in components. Okay, so that inductor actually then becomes the voltage source in this case. So it's kind of fun. Let's take a look at this in a circuit. So I have built this circuit in the PHYS circuit construction kit here. So I've got my power supply. I've got two switches in here now. I've got my resistor, and this guy right here, the solenoid, is my inductor. So if I just want to kind of look at like a current chart, and I just want to see kind of the current right here, so I can try to track that current through that resistor. So right now, there isn't anything going on. But if I close the switch to connect the battery, and I zoom out, I can see that I got this curve in my current. So instead of jumping up straight away, I actually slowly increased until I reached a steady state. All right, so I'm going to have to kind of break the simulation for a second in order to make this work right because I don't have a double switch capability with this circuit, so I can't turn those switches at the same time. And I tried pausing the simulation to make it work and it wouldn't. So, but if I want to then close the one switch and open the other switch to see what happens, I can see that just kind of briefly, I actually got that decrease. It doesn't quite work here, like I said, because I can't get the switches closed right. But you can see that when I created the short circuit over here, that just for an instant, that we actually had the that decrease in the current due to that inductor. So even though if I had done that, the current would have been just dropped completely. I did actually have that slow decrease in the discharge as that inductor resisted that drop when I created the short circuit. And that's why my battery caught on fire, is I have no resistance over the circuit on the left to kind of modify the current as that happened. So that gives you an idea of kind of how those behave. And just one last topic here are transformers. So transformers are going to be another application of kind of flux and solenoids. And we're not going to go super into detail on kind of how all these equations are derived, but they're kind of cool. So you might have seen transformers on the power poles. They are basically big electromagnets, and they have two sets of coils in them. So one side will have a high number of wraps, and then the other will have a smaller number of wraps. Because they are around the same core, they're going to have the same flux through the same area. And when we have the current that is running through the wire, due to the difference in the number of coils, you're going to have a change in the flux through them. Now, this actually is an application of alternating currents, because our actual power that comes through our walls is alternating current. And with that alternating current, it is more efficient to pass that through on high voltage. So you see all those high voltage warning signs. Is our power line transmissions are high voltage. If you were to run that high voltage into your house, it would be super dangerous because of the high currents that are possible. So that high voltage could be very damaging. So instead what they do is they use transformers to step down the voltage into your more usable voltages for your household. And then there are also transformers, well, not really, I mean, there's still, your voltage is then further stepped down to like your device. So the voltage that comes out of your outlet is a lot higher than what your like cell phone needs to actually charge. So there's a lot of electrical components in your big wall battery pack thing that step the voltage down even further to make it safe for the delicate pieces of equipment that are inside of your phone. So because we're getting this induction here, the induced EMF is the same in both of the coils, because the voltage has to be, the induced EMF has to be the same for both of the voltages. So what ends up happening is you get this ratio here. So your voltage 2 is your voltage drop across one of the wires, and N2 is the number of turns. V1 is your voltage across the other one, and N1 is the number of coils. So I can see that if I take a primary voltage here, and I have a number of loops, if I increase the number of turns, my voltage then increases. So if I go from a higher voltage to a smaller voltage, I have to just adjust the ratio of turns in order to step down that voltage. So we could have like a step down transformer, which is what I'm talking about here, like with the household. So that step down transformer has to go from a high number of turns to lower number of turns. If I wanted to step up, then I would do the opposite. So step down, you decrease the number of turns. Step up, you increase the number of turns. And there's this nice little ratio here to kind of help you with your calculations.